Most people think rainbows are just light bouncing around inside raindrops. That's partially true, but there's a hidden geometry that explains why you can never reach one. The real story starts not with color but with angle. When sunlight enters a raindrop, something precise happens. The light doesn't scatter randomly. Instead, it bends, bounces, and emerges at a very specific angle, around 42 degrees from the antisolar point. That's the invisible spot directly opposite the sun, behind your head. Step to the side and the rainbow vanishes. Move back and it reappears. Why? To understand this, we need to think about what light actually is. Light travels in straight lines until it hits something. When it strikes the curved surface of a raindrop, it slows down. That slowdown causes it to bend, a phenomenon called refraction. Imagine a car's wheels hitting mud. The wheels on the muddy side slow first and the car veers. Light does something similar. But refraction alone doesn't make a rainbow. Inside the raindrop, something else happens. The light bounces off the back surface it reflects. This reflection is crucial. It's not a gentle bounce, it's a full reversal, like a ball hitting a wall. Now the light is traveling back toward the front of the drop, bending again as it exits. That double bending plus the internal reflection creates the geometry that locks the rainbow into place. Here's where it gets interesting. White sunlight isn't actually white. It's a blend of colors: red, orange, yellow, green, blue, indigo, violet. Each color has a slightly different wavelength. And here's the kicker: each color bends by a marginally different amount when it enters the raindrop. Red light bends less. Violet bends more. This tiny difference, fractions of a degree, adds up after refraction, reflection, and the second refraction. Red emerges at roughly 42 degrees. Violet emerges at roughly 40 degrees. All the other colors land in between. That's not just separation, that's order. That's a spectrum arranged by physics alone. But why can't you reach a rainbow? Because it's not a thing, it's an angle. A rainbow is the collective light from millions of raindrops, all positioned at that precise 42-degree angle from the antisolar point. As you move toward where you see it, the raindrops behind you now fulfill that angle. The rainbow shifts. You're always chasing an angle, never an object. There's another detail worth sitting with. If you ever see a second rainbow outside the first one, that's light that bounced twice inside the raindrops instead of once. Two internal reflections. The angle shifts to about 50 degrees and something strange happens. The colors reverse. Violet is on the outside, red on the inside. The light has literally flipped its sequence. Between the primary and secondary rainbow, you might notice something odd. The sky looks darker. This region is called Alexander's dark band, named after Alexander of Aphrodisias, who observed it around 200 AD. Why is it darker? Because light is being concentrated into the primary and secondary rainbows, leaving less light scattered into that zone. Now here's a question that connects everything. If rainbows require a specific angle between you, the sun, and the raindrops, why do you see them at all? The answer is probability and scale. After rain, the sky is filled with billions of water droplets. Some are always positioned at the right angle. Your eye is always at the right position. The geometry aligns constantly, invisibly, without your effort. This is why rainbows only appear when the sun is behind you and rain is in front of you. Stand with your back to the sun, look at the rain. The angle between the sun, your eye, and the raindrops must fall into that narrow window. Step too far forward and the sun is no longer behind you. Step too far back and the raindrops are no longer in the right position. The geometry breaks. There's also a practical consequence of this geometry. Rainbows always appear in a circle. You're seeing light from raindrops arranged in a cone shape around the antisolar point, all at that same 42-degree angle. If you could see the whole cone, if you were in an airplane high enough, you'd see a complete circle. On the ground, the horizon cuts it off, so you see an arc. One more layer. The colors you see in a rainbow aren't quite the colors of the spectrum. Red is there, true. But the intermediate shades, the oranges, the yellows, they exist because raindrops of different sizes refract light differently. Larger drops produce sharper color separation. Tiny droplets blur the colors together. A rainbow is never quite the same twice. So when you stand in the rain with the sun at your back, and that arc of color appears in the sky, you're witnessing geometry made visible. You're seeing refraction, reflection, and the physics of light separated by wavelength. You're not looking at a thing. You're looking at an angle, shared by billions of water droplets, all arranged by chance and physics. The reason you can never reach a rainbow isn't mystery or magic. It's mathematics. The angle is locked. The droplets are always receding, and your eye is always in the only place where that specific geometry resolves into color. That's the everyday physics of the rainbow. That's why sunlight after rain becomes a spectrum. Subscribe so you don't miss the next ordinary phenomenon that turns out to be extraordinary physics.